time I give the. Okay.
Okay, stop at the gate.
Touch screen, touch that. Okay, it's the first time I give the CME talk in this seminar. So yeah, I will present the experimental search for the chiral magnetic effect in heavy ion collisions. Most people are familiar with this physics in the room, but I will give some brief introduction anyway. Then I will show some initial evidence when we were so excited to see the signal, then followed by no results or negative results, which is pretty devastating. But then more recently, there seemed to be reappearance of the signal. So we are excited again. And so that's how you deal with life. And in the end, we have an outlook. So the physics, the CME means chiral, you need to have a chirality balance. So which means you have either more left-handed or more right-handed quarks. Magnetic, you need a strong magnetic field. If you have both of them, they can induce an electric current. But this is not just some high school physics, right? If you have Faraday effect, the magnetic field can induce the electric field, but it's different. In that case, they are perpendicular to each other. But the CME, they are parallel to each other. So a simple illustration is the magnetic field is, if it's very strong, it will align the spin or anti-align the spin of particles. And according to the electric charge, then I think probably something is, okay, this is all U quark, so that's right. So U quark has positive charge, and as a result, spin should follow the magnetic field direction. But if it's D quark, spin should be pointing down. Then if we have more right-handed quarks, that means momentum will follow spin direction. So as a result, you will see an electric charge separation in the same direction of the magnetic field. But if you have more left-handed particles, the J direction will be reversed. So in heavy ion collisions, do we have such preconditions? We do. So when we have QGP and the chiral symmetry restoration, quarks become almost massless. So only when quarks are massless can we talk about finite or definite chirality. For massive quarks, the chirality will oscillate from left to right and back and forth a long time. So you cannot talk about chirality of massive quarks. Only in the QGP and only when chiral symmetry is restored can we talk about that. And then there are some mechanisms, we call them vacuum transition of the gluon field. And in this case, so this is the potential energy of the gluon field. And each state is represented by a Chern-Simons number. If it happens that this configuration can go through, so if there's vacuum transition, either through instanton or sphileron, then during this process, quark can obtain some finite chirality, and this is through the so-called chiral anomaly. I will skip the details, but through the vacuum transition, we can have a finite chirality for quarks, and that means μ5 can be non-zero. And then the other precondition is the strong magnetic field. So in heavy ion collisions, the very energetic spectators, when they pass through each other, they will generate the strongest magnetic field on the order of 10 to the 14 Tesla or 10 to the 18 Gauss. So that's probably the strongest magnetic field ever observed by us. Then all the preconditions can be met in heavy ion collisions, and we could have the CME in the collisions. The only thing is, can these conditions happen at the same time? So if they don't happen at the same time, we still won't have the CME. So that's probably the biggest issue for us.
It's not quite clear whether the color imbalance actually can be satisfied. The mu phi is non-zero. It's not clear whether it has to be non-zero, right?
Yeah. So yeah, it's according to the theory. There could be vacuum transitions. Also, those different states are energy degenerate. So there's no nothing preventing them to happen. And they could go through tunneling called instanton or jumping over the barrier called sphileron. According to Dima and the theorists, in heavy ion collisions, it's more likely sphileron will happen and we will have the vacuum transition. So the CME observable. Since we are searching for the charge separation along the B direction, and in the experiment, B is perpendicular to the reaction plane. Reaction plane is the beam momenta and the impact parameter. They span the reaction plane. So instead of looking at the B direction, we look at the reaction plane direction. So if we expand the particle azimuthal angle distribution with the Fourier expansion, this A1 term in front of the sine, first order sine harmonic, that can represent the charge separation because A1 can be bear opposite sign for opposite sign particles. For example, positive particle can go up, negative particle go down, and it can be quantified by this A1. Then the question is, do we want to really directly measure this A1? The answer is no. If you directly measure this A1, you average over many events, you get 0. And that's because the vacuum transition, if it ever happens, it has the same possibility to go left or right. So it's a parity odd quantity. If you average over many ensemble, you get 0. So what we do is we have to look at the fluctuation, event by event fluctuation of this quantity and compare it with some baseline. If we have some actual fluctuation, it means you have evidence of the charge separation. So on the market, we have several popular CME observables. The first one is the gamma correlator. I will explain more later. And also the R correlator, the sign balance function. So every time people invent a new correlator, a new observable, they claim it's a better one. And the old one is like rubbish. However, in a recent method paper, we show that actually all the three methods, if we just examine the key component, they are sensitive. So if we plot the key component of the three observable together as a function of the true signal in AVFD models, they are just identical in terms of the true signal. So they are sensitive to the signal, but they're sensitive in the same way. Also on the left, it shows that the x-axis is the input of the signal strength, and the vertical axis is the key component of the observable. So even at 0 input, you have finite signal, which means not signal, they are background. And all the three methods actually see the same background. So this method paper proves that all the three methods just have the same sensitivity to both signal and background. So we should not argue about which one is more advanced, which one is less. They are actually just equivalent. And this paper, actually Yu is also a PA of this paper. This paper won the best paper award this year in Chinese Physics C, because this is really important. It stops the argument over many years. It saves us many time and effort.
You still depend on who you ask.
Yes, but the message I want to deliver to the general community is, yeah, they're just the same method with different variants. Yeah, there's some subtle difference, but basically the same method. So I will focus on the gamma correlator. Oh, now we call it gamma 1, 1, 2. 1, 1, 2 represent the harmonic number before this phi alpha, phi beta, and psi. Phi alpha and beta represent the two particle azimuthal angle. Alpha and beta could be positive or negative. And the psi 2 represent the reaction plane. It's called second order event plane. And so the CME signal, if there is a CME, it will make delta gamma, which is opposite sign minus same sign, positive. Although when you see it's positive, it doesn't necessarily mean it has to be CME. It could be some non-CME background, which is the thing I want to deal with. But in the following slides, I just focus on this observable because it's the simplest and most widely used. So initial evidence. So in the beginning, we were pretty happy about the measurement. For example, for gold-gold collisions at 200 GeV as a function of centrality, but 0 means most central and 70 is peripheral. And we have also copper-copper, gold-gold and the copper-copper. The blue points are the opposite sign and the red points are the same sign. So you see opposite sign is above the same sign. That means if you take a difference, you see a positive finite signal and indicating charge separation. Also, uranium, it looks almost like gold. Probably it's like a bigger gold and the similar charge separation signal. Also, we go through the beam energy scan and I put the RHIC result in the first panel. So everywhere, almost everywhere, you see the separation between opposite sign and the same sign. And until 7 GeV, so even at 7 GeV, if you take a closer look, take the difference, for some centralities, we can still see some finite difference. And a feature I want to point out is when you go lower and lower energy, both opposite sign and same sign tend to go up towards peripheral. And this is just momentum conservation coupled with V2. So it can be reproduced reasonably well with a simple model called MAVSIM. MAVSIM has no CME. It's just V2 and the momentum conservation. And if you look at the gray curve, it qualitatively explains this trend. So that's why we should not just look at opposite sign or same sign separately. We should look at the difference. The difference will cancel out momentum conservation background. So up to then, we were pretty happy. But the question is, we cannot be over-optimistic. Even though we see some finite difference, they could be related to something non-CME. For example, flow-related background. That's proportional to elliptic flow, the second harmonic of the Fourier expansion. Or there could be even non-flow background due to resonance decay, dijet, momentum conservation, and so on. So we have to deal with this before we claim victory. So our early attempt to mitigate the background is we want to compare our measurement with some model. And the model has no CME, so which is pure background. To do that, we need to normalize the delta gamma because the model may not be perfect. It may not reproduce everything. But this normalized quantity is a better comparison. So we normalize the delta gamma by V2 and the delta delta. Delta is just two-particle correlation. The two-particle correlation can capture things like decay, momentum conservation, jet. So the thing we want to compare is at that time, we don't have AVFD. So the best one we have is AMPT. AMPT can reasonably well describe RHIC spectra and the V2 and some other correlations. So around 10 years ago, this is the best thing we can have for background estimation. So this figure shows the comparison of the kappa. We call this kappa 112, which is just a normalized delta gamma. And the gray band represent the AMPT simulation. And AMPT, again, it has no CME, it's pure background. So at LHC energy, everywhere the measurement and the model agree with each other. So that means everything measured by Alice can be explained by pure background. And at RHIC, actually 200 GeV, 27, we can see some excess of the measurement over the background. If we go further, actually, I think I should update this figure. We have more comparison in a more updated figure, but the essence is the same. At 7 GeV, again, the measurement and the model calculation are very comparable. They are consistent with each other. So at that time, we can learn some preliminary information about the background. So it seems at very high energy and at very low energy, we do not see any signal, or we should not. Only in the middle, we may have some hope, although we are not guaranteed that these are CME, but we have some room for the CME. At very high and very low energy, we don't even have such room. Then how can we explain this? At very low energy, it's easier to understand. People can argue that chiral symmetry is broken at very low energy. Then you don't have μ5, you don't have CME. However, LHC, they should have chiral symmetry restoration. So the argument is the magnetic field may disappear so fast at very high energy. The reason is like this. So this is just a simple formula calculation for the magnetic field. The x-axis is time. The vertical axis is the magnetic field. So at very early time, if you look at 2.7 TeV represented by the red curve, indeed, it is like 13 times higher than 200 GeV, which is reasonable because magnetic field should scale with the collision energy. The peak magnitude scales. But in the vacuum, this magnetic field drops very, very fast. So by the time of 0.1 Fermi over C, where we think quarks are not created yet, but this magnetic field at 2.7 TeV already dropped like 2 orders of magnitude below 200 GeV. So this is the reason we need the preconditions to happen at the same time. So if by the time you create QGP, the magnetic field is already too weak, then it cannot initiate this CME. So this can explain why at very high energy, we should not expect the CME to occur. It just dropped like a stone. When you go lower energy, like 20 GeV, 5 GeV, in the aspect of magnetic field, they are probably still fine because in the vacuum, the magnetic field at lower energy can last pretty long or much longer than high energy. So that's why I don't expect LHC to see it. Yes.
Yeah, for this AMPT calculation, it seems there are no energy dependence. Is there any Q2 explanation or what background?
Because the background is just a coupling between V2 and some other effect. And this coupling strength is like a constant. So what we are looking at is like a coupling strength. Then when V2 change, delta gamma change, when V2 change, delta change, due to background, the delta gamma will change for different energies. But this strength is always the same due to the background mechanism. So that's our understanding. But we cannot be satisfied by this excess because in peripheral especially, it even goes up. And it could be due to so-called non-flow effect. And that's something I will mention soon. So again, I want to review the development of the experiments. So a few years ago, we proposed the isobaric collisions. The idea is zirconium and the ruthenium, they have the same number of nuclei, both 96, but one of them has only 40 protons, the other has 44. So the charge is 10% more. That means the magnetic field is 10% more. And our measurement, that gamma is proportional to B squared. So that means almost 20% more in signal. But then consider the fluctuation and so on. So we expect if we collide them at the same energy, then ruthenium should see about 15% larger signal than the zirconium. So this is good if the fraction of the CME in delta gamma is large enough. So this is the figure I made at that time as a projection. The difference between so this R means it's a ratio. It's a ratio between the two system, delta gamma, minus the eccentricity difference. It can be related to the magnetic field and the eccentricity difference and linked by the background level. So at that time, we proposed to have 2 billion events per species. And if the background level is around 86%, that means if the fraction of CME is bigger than 14%, then 14% times this 15%, it will give us a 2% difference, relative 2% difference between the two isobars. And we estimated the statistical uncertainty is about 0.4%. So that means the precision, when we have 2% over 0.4%, we will have a 5 sigma discovery. So that's a hope. If the CME fraction is larger than 14% in isobaric lesions, we should see a 5 sigma effect. Then we have a discovery. Although in the end, the reality is very cruel. But at that time, we don't know the FCME. So we can only hope we have a bigger FCME. So in the end, whatever nature gives us, we have to accept. So this is the final result. So STAR went through a blind analysis. So meaning we have to design all the procedure beforehand. And then everything is frozen. The code is frozen. The procedure is frozen. So no one can change anything. Even though you find something wrong, you cannot change it. And so that's good and bad. The good thing is it's very strict and there's no human error of it. The bad thing is we may really find something wrong in this complicated things. So the baseline is 1 for the ratio of ruthenium over zirconium. So our initial expectation is if you see a ratio being 1, it means no CME. If you see the ratio above 1, you have some signal. But what we saw was the ratio is below 1. So this is hard to understand. And then we go back and check everything. We found that the multiplicity is mismatched between the two isobars. So we were matching centrality. But when we match centrality, when we design the procedure, what we have in mind actually was multiplicity should be the same. And then in reality, they're not the same because ruthenium is a little larger than zirconium. Then for the same centrality, there is a multiplicity mismatch about 4%, 3% level. And this multiplicity mismatch will cause the baseline to shift down. So recently, STAR re-estimate in the post-blind analysis. We re-estimate the baseline, which is the shaded bands. And again, so all the measurements are consistent with the new baseline. So that means we do not see the signal. Although it's disappointing, it's more reasonable and acceptable. Another way is we can just try to do it right. We can just match multiplicity. So that's the 3 points on the right. This is newly presented in the quark matter conference. So when we force multiplicity to have the same distribution between the two isobars, we see the ratio are highly consistent with unity. So again, it means no signal, but it's reasonable. It's a successful failure.
But if you match,
yes.
if you match multiplicities, the centrality being very different. And
so first we select the same centrality. Then within the same centrality, we force match the multiplicity. But anyway, in this physics, multiplicity is more crucial than centrality. So, okay.
But in
yes.
that case, can you still, even though in this match, can you still have confidence that the magnetic field is the exact same up to that precision?
So the magnetic field should be different, should still be different, right?
I know, different was what you expect,
yeah,
but it could be
maybe slightly different than expectation.
Yeah.
Yeah, but that's that should be a small effect. It could be like when you expect the magnetic field to be 15% initially, but now you have 13%. It's that level. It's not like it will disappear, right? But yeah, I will come back to such point also later. Then why is the fraction of the CME so small? Because this consistency means the FCME is around 10% or lower than 10% level. Then when you convert it, even if you have some signal, it's hidden by the error bars. So why is it so small? We should have noticed this earlier, but we didn't. So it's kind of something we ignored in the beginning. The reason is we run some AVFD simulation with the input signal, the x-axis, N5 OS is the input CME strength. And the upper panel is the FCME measured with the true reaction plane. And the lower one is measured with the participant plane. So in the isobar analysis, we used participant plane. And when we do the estimate, we used the reaction plane. So when we have look at the reaction plane for gold, because the previous projection was based on gold, we didn't have isobar when we proposed isobar. So if you look at the black point in gold, it corresponds to a much lower fraction for isobar if you use participant plane. So there are two factors. The first factor is when you change from a large system to a smaller system, the fraction reduces. The other factor is when you change from reaction plane to participant plane, there's another factor. So if you consider both factors, it's about a factor 3 or 4 reduction, changing from gold to isobar, from reaction plane to participant plane. So that's why even if in gold 200 GeV, if we use reaction plane, we see something like 20%, and you convert it to isobar with spectator plane, you will see only a few percent. Then that a few percent, you multiply by 15%, it gives you something consistent with 0. You won't see it. So that's basically the reason. The smaller system involves larger fluctuation, and that means larger background, smaller signal. So it's a double kill of the fraction of the signal. So that's why we want to focus back on large system like gold. Yeah, I will also come back to this point a little later. So now I want to talk about the background. First, non-flow background. So non-flow related background, initially we talk about it only in V2 measurement. For example, this is V2 measured with some event plane. If we use the PPC event plane from the same rapidity as the particle of interest, you have a large non-flow. But if you use BBC, which is pretty forward, you suppress non-flow because many non-flow are short range. So if you compare these two results, ideally they should be the same. You are measuring the same V2 of the same particle. However, only in more central and mid-central, they are pretty close to each other. We'll go to peripheral and the P-gold, D-gold. You'll see a large discrepancy between these two methods. And that means non-flow effect. Because non-flow, by definition, is some correlation unrelated to the reaction plane. So if you use two different planes, you see different results. That's non-flow. So only when you use BBC, you see some reasonable coming down of V2. If you use TBC, they even go up, and that's abnormal. That's not true. So this is how we can tell a non-flow effect. You just use two different event planes. BBC is forward, TBC is mid-rapidity, and you see this huge difference. In the same way, we look at the delta gamma multiplied by n part, just for easy display. You see in central collisions, they're pretty close to each other using different planes. But when you go peripheral, you see huge difference. If you use the forward event plane, the signal should disappear. And indeed, it disappeared in P-gold, D-gold. And we do not expect any CME in such system, because in P-gold, D-gold, even if you have magnetic field, the magnetic field direction is decoupled from the reaction plane or from the event plane. They are random to each other. Then you should not see anything. However, if you use TBC, you see a large signal. So this also represents non-flow effect. So how can we control this? We have to use some forward detector to determine event plane. For example, BBC is 3.8 and beyond. And later in lower energies, we have event plane detector, which serve the same Fourier functions. So technically, we can control the non-flow effect. The flow-related background is harder to remove. So let me give you one example to explain why flow can give you background in the CME. So this is a very simple example. In one event, you only have 4 particles. Positive, negative particle go X direction. Another positive, negative charge go backward. In this case, apparently there is no charge separation. They are all sticking together. But you have a large V1, V2 is 1. And if you, based on the combination, you calculate opposite sign of gamma, you get -1. And opposite sign is 0. So delta gamma is 1. So it seems to show a very large charge separation. Actually, there's no. Apparently, we don't see any charge separation. So this is because V2 is coupled with the 2-particle correlation. So either this is from decay or jet or cluster. They can be coupled with V2 and give you a fake signal. So this can be controlled if we can reduce V2, because this effect is proportional to V2. And there are also some so-called hidden anisotropy. So from the appearance, you do not see any V2. You still have 4 particles, and you put them in 45 plus minus 45 degrees. And in this case, you actually see some charge separation. But this charge separation could come from decay. So if both in this direction, there is the Ru meson going this way, and they decay into pi plus, pi minus, it can fake a charge separation. So in this case, the V2 of the final state particles are 0, but still they can fake some finite delta gamma. So this thing, you have to control it for the parent V2, not just the daughter V2. So this is harder to control. But in the end, we figure out some way to get rid of all these situations. Now I want to review some early attempt from STAR on the event shape engineering. So the meaning of event shape engineering is we want to control V2. And V2 is related to initial eccentricity of the geometry of the collision. So if we can select some spherical events, or if we can project the events to spherical, then V2, whatever V2 will be 0. No matter it's single particle or resonance or the decay daughter, they should all, on average, give you 0 V2. However, this is not a successful attempt because the vertical axis is something equivalent to delta gamma. So this is another observable, and in the end, it's turned out to be equivalent to delta gamma. So just consider this is delta gamma. The thing is the x-axis. So this paper, they directly use the so-called observed V2 without any binning using flow vector. I will mention later. So by doing this, this is not really V2. It's just a correlation between two sub-events. So the two sub-events can fluctuate and give you 0 correlation or even negative correlation, but it could have nothing to do with V2. So you thought you project the measurement to 0 V2, but you're not. You're looking at something different. How can I put this back?
Yeah.
Okay. So we wrote a method paper to explain this. With even a simple model, we see that this is the true V2. And the x-axis is this observable, the so-called event-by-event observed V2. So the upper panel shows that when this observed V2 go negative, actually you see a U shape. It's not monotonic. And the true V2 can never be 0, no matter where you are in this observed V2. So it doesn't represent V2. And what is worse is if you look at the event plane resolution, the resolution can go negative when you use such an observable on the x-axis. So that means this observable cannot be corrected by event plane resolution. And indeed, when Star published this, they didn't correct for event plane resolution because there's no way they can correct it. So this is a failure in the methodology. And yeah, so I have explained all the disadvantage of doing such an attempt. So we should do something better than this.
Can I ask a question on the right figure? So
Yes.
which data points corresponding to what kind of categories of events on the right figure?
So the x-axis are the same for the two figures.
But the V2 is just the
V2 is the true
physical, but
the true V2.
True V2.
Yeah, it's a true V2 calculated with the reaction plane. So this is the reality, and this is what appears to be.
But I saw the V2 is basically just x-axis for a group events, our mean value of the x-axis. Correct for the resolution.
No, yeah, correct for the resolution. But you see the resolution change sign.
But I don't understand the exact data point. What do you mean? It is the x-axis is just a event kind of a characteristic, the shape of the topological distribution.
In some sense,
right,
it's only called V2.
Yeah.
It has nothing to do with V2.
Sure.
It's a correlation between two parts of events.
Okay.
And yeah, you have to correct this with some non-trivial resolution to make sense, to make it physical. So currently it's not really physical. Yeah, that's the reason. If you correct this, then points will be moving around to be right. Yeah, so no one ever uses again, ever, because it's wrong. The right, one of the so-called standard way to do event shape engineering is you should divide an event into 3 sub-events. And first one is for particle of interest, where you calculate your V2, you calculate gamma, and so on. And the other sub-event is for the event shape variable. We call them Q2. This is to control the event shape and to classify or categorize the events. And the third one is the one we use for the event plane. So in the so-called standard way, you need 3 sub-events. And the flow vector is defined in this way. It's just the flow vector we use to estimate event plane, except we normalize it with the square root of n. So this is at least measurement when they select events. So each point is selected based on a Q2. Then for that Q2, they measure gamma, they measure V2, they plot one against the other. So in this way, they try to project it to 0 V2 to find the true signal. And in a similar way, but not exactly the same way, CMS did this for finer centrality beams. And again, it's the delta gamma against V2 selected by a separate Q2. The issue with this standard way is there is a big open blank space between the data point and the 0. So when you try to do the extrapolation, it's a long shot. And this gives you a large uncertainty, both statistically and systematically. We're not even sure in this blank region, is it really linear or not? We don't know. So this gives huge uncertainty. And the extrapolation is unstable.
The uncertainty is from the data points, right? Not the extrapolation.
That's
if you are extrapolating with a straight line, it should.
But you only have data points in this region. And you want to know something here.
Right,
so
but,
you have to assume over this area it's linear.
yeah, that's an assumption.
Yes.
And but if you make that assumption, the error bar is driven strictly by the data points, right?
Yes, it is. Well, I will show a little more of this. So it gives you unstable results. I'm not saying it's wrong. So this method is okay because it tries to control the eccentricity with a separate Q. However, in practice, it's very hard to give good results. So I try to explain with the AMPT simulation. So this panel, the vertical axis is the V2 of single particles. The x-axis is that Q. We call it Q2B, meaning B is a separate sub-event from particle of interest. So you see, even when Q is 0, this V2 is finite and pretty large. So that's why when you plot delta gamma as a function of Q, there is this open space. And these three panels represent the three input of the signal. N5OS equals 0 means pure background. And this is a moderate signal. This is a strong signal. So the first thing you see is if you do the extrapolation with the linear, you have some over subtraction. Then if you want to test, is this really linear? You try a second order polynomial. It gives you some finite signal, which is background. And then in the other two cases, when we have signal, we can project the signal to 0 also. And they do not always meet. They cross each other. That means over subtraction. And also, if you involve a test of second order polynomial, you have a huge over subtraction. So that's why I say not just statistical error is much larger. Systematically, it's not stable. And it's really hard to overcome such an issue if you insist particle of interest should be excluded from Q.
The red and blue here are
what?
The red and blue here are.
The blue is the observable of delta gamma, and the red is the true signal. Because this is simulation, we know what is the true signal. So that's why we try to develop a better way to do this. So ideally, if we can control eccentricity, we control everything. However, even with the same eccentricity, the final state particle emission can be very different. We have very large fluctuations of the particle emission. And the final observable of delta gamma is subject to the particle emission. So even though you have the same eccentricity, the different emission can give you different background. So that's why we should focus more on the particle emission. And to do that, we want to include the particle of interest into the Q, into the flow vector. And another reason is there could be so-called decorrelation. If you select Q other than the rapidity region for particle of interest, there could be decorrelation between them. And then this Q doesn't really represent the same eccentricity. It represents a different eccentricity. So this is our study. We try to select particle of interest and use particle of interest to build the flow vector. On the left is just Q or Q2, the distribution of Q2. And if you look at V2 as a function of this Q2, it can go to 0, almost 0, 0. So this is technically very effective. And then in this method paper, we found that actually Q2 square is a better observable. It's a better control over the event shape because the distribution of the Q2 square has a peak around 0. It's just due to the Jacobian effect, but we can take advantage of this effect. If we plot V2 against Q square, it also goes 0, 0, but it's more like a linear projection. And technically, this is better. It's a better lever arm. But in this one, it's more flat, not as effective as Q square. And also, at that time, so initially we use AMPT to test the method. So we use our Q square to select events and then plot delta gamma as a function of V2. And this is for one centrality, 30 to 40%, with both reaction plane, true reaction plane, and the persistent plane. So actually for AMPT, in both cases, we have over subtraction. And then if we look at this intercept as a function of centrality, in some centrality, it's good, it's 0. And in some centrality, it's slightly negative compared with the previous ensemble average. So this seems to tell us that AMPT doesn't describe the background so well. It can describe some background, like resonance decay, but momentum conservation is already not perfect in AMPT. And local charge conservation is not specifically tuned for AMPT. So when we use even a simple way to do this projection, we over subtract. Then we look at the AVFD, which is a more realistic model because it not only built in CME coherently, it's based on hydrodynamics. So momentum and the energy are conserved. And also this specifically tune local charge conservation to match data. So this is up to now the best model we can use. Then what we see, the upper panel is using reaction plane, lower panel is using participant plane. And the x-axis, when 0 means pure background. So even for pure background, our method, the initial test, the method doesn't remove all the background. There is slightly residual background, even when there's no signal. Although we do suppress the background by a big factor, maybe a factor 5 or 8. But it's a little disappointing because we do not remove all the background with this method. Also, when you have a signal, you can remove a large chunk of the background, but this curve represents the true signal, and the final observable are still above the true signal. So meaning our simple event shape selection still have residual background. We still need to improve this method. Yeah, okay, I'll be fast. I'll be, but I have the seminar is until 5, right?
Oh, 1 hour.
No.
Okay.
1 hour.
Okay, I will speed up. So, okay. So to solve this, we try to consider the special case. The special case is you only have two daughters, decay daughters, and the two decay daughters go 45 and negative 45 degree. So in this case, they do not contribute to your flow vector, because if you calculate this, they give 0. However, this is a charge separation faked by a decay. So we need something that can capture this scenario. That's why we introduce pair information. So if we use particle pair defined in this way, and this can capture such a scenario. And not only for the Q, we can use particle pair. For the V2 observable, we can also use particle pair. So altogether, for the flow event shape variable, we can have single or pair Q. For elliptic flow variable, we can have single and pair V2. So we have 4 combinations now. Previously, we only have single, which doesn't seem to work well. And then we understand there is some self-correlation if you do single, because if you expand this Q square, and in the end, you get Q square average is related to V2. So if you plot delta gamma against V2 binned by Q2, there should be some self-correlation. So we need to correct for that by using pair Q2. And also, this is not exactly one, meaning the definition of Q2 needs some correction in the normalization. So this is an improvement in the normalization. And then, okay, we use some toy model to study the background effect. So according to Sergey's paper, the background due to resonance decay is just V2 of resonance times the internal correlation between the decay daughter and the cluster or the parent. So indeed, when we check this effect, we use the toy model. The upper panel is show V2. The middle panel show this factor. Then we multiply them and compare with the delta gamma background. They agree very well. So that means this picture is right. The formula is right. We can use such thing to control background. However, we cannot use resonance V2 to control background. The reason is, in the experiment, we use invariant mass to reconstruct resonance. And even this invariant mass distribution is influenced by CME. So this is something striking to us. So if you have CME, the invariant mass distribution will be modified. And also, if you look at resonance V2, it increases with the input of the CME signal. So that means resonance V2 actually is a CME observable. It's not just a background indicator. So like in this case, if you look at resonance V2, in different cases, background subtracted, it's linearly proportional to the input A1 square. So that means resonance V2, we can actually, in principle, we can use it to measure CME, although it's not efficient, it's not effective, but it's sensitive to the CME. So if you use resonance V2 to do event shape, you will have severe over subtraction. And we explain it in this paper recently published yesterday by Joan in our group and other people. So we cannot use resonance V2, but in the same idea, we found that we cannot use pair V2, because pair V2 also contains the CME signal. So we run some simulations, because I mentioned we have 4 combinations: single, pair, single pair, and pair single. So in the end, we found that the best way is using single V2 and pair Q2. This gives a perfect intercept that match the true signal. And at the same time, AMPT just doesn't work. So I will quickly go through the experimental results. So compare with B-scan1, now we have more than 10 times or 20 times more data. And we can use the new method to get rid of flow background. We use the event plane from EPD to get rid of the non-flow background. So this is the example of 19 GeV. When we do this method, delta gamma against V2, classified by pair Q2, we see some finite intercept for one centrality. Then we can look at different centralities with the 4 different methods. The upper panel is the delta gamma times n part. Lower panel is the ratio of the new result over the ensemble average. But let's just focus on the optimal method. So this is the optimal method. In some centrality range, we do see some finite signal. If we average this ratio, it's a 3 sigma effect. On the other hand, we use gamma 132 as a background indicator, which is pure background. So after event shape, they are always consistent with 0. So it means the method seems to work. Then we also did this for 27 GeV, 14 GeV, 7 GeV. I won't go through these details. Let's come to the money plot. So this is the 4 data points before the event shape selection. And the blue points are the after event shape selection. So we can see if you look at this fraction, it's around 20%. So that means the method at least remove 80% of the background. And this also explains why isobar, we should not see the signal. Because if you take 20% as FCME in gold, you convert it into isobar, you will get, in the end, the FCME in isobar should be around 5%. Then the difference between the 2 isobar is only 0.7%. But remember, the error bar is 0.4%. So that's why we should not see it in isobar. And almost the end. So actually, we have more data points, but I'm not allowed to show it because they're not star preliminary yet. But you can look at this curve I draw by hand. This roughly shows what you should expect in the very near future. So what we see is 11 GeV is still there, but then suddenly around 9 GeV, it disappeared, and it keep disappearing at 7 GeV. So, and on the other hand, the background indicator is consistent with 0. So why does it disappear at very low energy? Maybe no QGP, or maybe QGP is there, but chiral symmetry is broken because this is very low energy, but with pretty big μb. When baryon chemical potential is high, you can still have QGP, but if the temperature is not so high, you don't have chiral symmetry. So
it also seems to disappear even in the higher energy.
Yeah, in higher energy, it should also disappear. We don't have such measurements yet. I'm working on that actually. But the trend should be right. At 200 GeV, I have some results. Let's show in a smaller fraction than this.
But if you look at
Closer to 0.
the error bars, it's 1 sigma from the
Yeah.
14.6 and the 19.6.
Yeah, this error is pretty large, but 9 GeV is smaller. And then we also try to, the last slide, I think. Yeah, so if we combine the 3 points, we could have a 5 sigma effect. It's just, we need to think about how we can combine such points, right? Because each point is 3 sigma. So if there's no such signal, then it means you have a small chance to be wrong because of 3 sigma. Then if you are wrong 3 times with 3 small chances, combined, it's a small chance corresponding to 5 sigma. So in that way, we can combine the information at least. Also, in the future, we have 17 GeV. So there's no reason it will suddenly drop that, right? So I would expect, again, something like 3 sigma signal, although we haven't checked this, but this is something on the agenda. Then future, we want to do 3 GeV, because if it's true that it disappears here, then it should keep staying 0. So that's something we want to try. And the explanation, one possibility is deconfinement and the Chiral's transition may happen at different time or different temperature, or in the same collision, one is there, the other is not, due to some physics. So the rest are not important, so I'll just stop here.
Yeah. For comprehensive and exact result, do you have any questions? Or any question online?
So why do you think there's at 9 GeV there is a sudden?
Oh, because we have the measurement, so I know.
I know, but physics-wise.
Yeah.
If you think it's due to some kind of onset of confinement, deconfinement,
Right.
this is the highly fluctuating system. You don't have like suddenly there is like onset of deconfinement, because at low energy there's fluctuation. There could be also high band.
The deconfinement could still be there.
Yeah.
But
so I don't.
Chiral symmetry may
So why there should be such a sudden transition as function of energy? That's what I don't understand.
I also don't. I'm a experimentalist. I try to report what we see and have some speculation to be verified by the theorists.
Is the 7.7 also BES2 data? Or is
Yeah,
that,
yes, it is.
so it has event plane and everything in there?
Yes,
like the
yes,
other ones, okay.
right. So all these are measured in the same way.
Okay.
Yes. Right. So looks promising, and we are still working on it. We try to, in the end, come up with a finite signal. But the way to convince people that the method really works is we need to find somewhere the point is highly consistent with 0. That means we really get rid of the background.
But you never know why you don't never know where it should be 0.
Right. Well, for
Because
example,
you also don't know where it should not be 0.
Yeah, but if we observe several points, one after the other at 0, and then pretty confident. Yeah, we are pretty confident.
Well, I mean, you said that analyses should always be 0.
Yes, yes. I will see. So, but we hope they can apply our method, right? If they get 0, then it's good. Also, I'm working myself on 200 GeV to see how low it can be, but at least up to now, it's lower than these energies. It's lower than 10%.
We also have 54 high statistics, right?
But we don't have EPD yet. We need that event plane to suppress non-flow. So 200 GeV, we can use CDC to do that.
So is this method easily portable to fixed target?
It's not so easy. Not so easy.
That's
Yeah, we are
more,
still thinking about the technical details, because fixed target is contaminated with one side of the spectators.
Exactly.
The target spectator is still hanging around and then contaminate the tracking and everything. Yeah. Also, we have only one side of the event plane, so that involves some momentum conservation effect. But I think nothing is a showstopper. We can overcome those.
Do you have a question online?
I have a question.
Yes.
So for the red point, so your default delta gamma, is this consistent with S1? Because I remember when you go lower energy in S1, the magnitude of delta gamma did decrease quite significant in the previous.
Actually, your impression comes from the so-called H coordinate, where we subtract the background. So if we don't subtract the background, they are similar. Also, at that time, we are looking at all hadrons. Now we realize that proton could be pretty different from pion and kaon, so we exclude protons.
Oh,
Yeah, because proton, antiproton can be very different, and just due to the finite mu b and large mu b, so we exclude protons.
That's pretty easy.
You don't exclude lambda or any decay.
We use primary particles, so that suppress the secondary particles.
No question. Thanks, go again.
Thank you.